Hey folks, welcome to our new unit, Energy Changes, and our first lesson, Thermochemistry. So what is thermochemistry? It's the study of the energy involved when we're talking about chemical reactions, physical changes, or nuclear reactions. Now we are going to be looking at all these individually as we move through the unit, but what you have to recognize is that nearly every single chemical reaction occurs with some kind of interplay between the absorption of energy and the release of energy. So let's take for example, we were looking at types of reactions a while ago, and let's say we had a compound A and compound B, and we had some kind of double displacement reaction where we created compound C and compound D. Now, in a compound like this, let's say for example, this is NaCl. Okay? So NaCl is held together by some kind of bonds. Now, since this is a metal and a non-metal, this will probably be an ionic bond. And so to split up the Na and the Cl to create two new compounds, we're going to have to actually break that bond altogether. Now, breaking that bond requires energy. So that energy has to be absorbed from our environment or any other kind of source. Now, when it rearranges and forms maybe Na over here and Cl over here with its new anions and cations, it's going to form a new type of bond. Now, it could be an ionic bond, it could be a covalent bond. It doesn't really matter, but whenever it forms a bond, it releases energy as well. So in breaking them, we absorb, and in forming them, we release. So thermochemistry is the study of this interplay between absorption and releasing of energy. So the types of changes that we saw, and we just briefly spoke about them here, and this is just a brief introduction, is a physical change which might look at the form of a substance and the change. And the form of a substance is usually due to the intramolecular forces. So remember, intramolecular forces will be things like London dispersion forces, dipole-dipole, and things like hydrogen bonds. So these are the forces in between molecules. So again, if we had molecule A, for example, like CO2, and we had molecule B, again, CO2, it's not the bonds that are formed in between. So let me just get rid of this. If we had, for example, CO2, and we had our oxygens doubly bonded like that, these bonds in here, those would be called our intramolecular bonds, and in this case, this would be a covalent bond. However, the physical properties and the way things look, whether or not this CO2 is acting as a gas or a liquid, for example, is actually due to the forces in between these molecules, and those are your intramolecular forces. Now, because this is CO2 and this is nonpolar, what we're going to expect is that these forces are London dispersion forces. Now, a chemical change is when we have a rearrangement of the atoms to form brand new substances, and this is due to the breaking and formation of those intramolecular bonds. So it could be covalent bonds, it could be ionic bonds, and so on and so forth. And then nuclear change is again an energy change, but it has to deal with the nuclear structure. Now, up to this point, we've only looked at physical and chemical changes, but we are going to be briefly talking about nuclear change and what it means to go through something called decay, alpha-beta decay, fission, fusion, for example. And this has to deal with the actual nuclear structure of our thing. So we're actually going to be going into the nucleus and looking at the protons, neutrons. So what we're going to look at is a few different definitions, primarily thermal energy, heat, and temperature. Now, some people use these kind of interchangeably, but they are not supposed to be used interchangeably because they do have different meanings. So the first thing is thermal energy. It's the total internal kinetic energy within a system, and it's caused by the motion of the molecules. So you can see there's a few different examples here of how these molecules can be undergoing some kind of motion. So when we look at, for example, just the molecule itself, these bonds could be going bendings or some kind of stretching, either symmetric or asymmetric stretching. This is called vibrational motion. So the molecule is vibrating back and forth, up and down, whatnot. So there is some kind of motion in there. The other type of motion that we have is rotational motion. Okay? And so it could be kind of a movement this way, so the molecule is spinning on this axis over here, or it's spinning on this axis over here. So again, there is some kind of motion, again, kinetic motion there. Or we have translational motion, which means it's going in a pathway like that. Now it could hit a wall and bounce back or something, whatever. And as it goes through translational motion, it could also be spinning and it could be vibrating at the same time. So we do see this motion in three forms. So the thermal energy is just the amount of kinetic energy in this type of collection of molecules that are undergoing all these different types of motions. So as we saw, all molecules possess some form of kinetic energy. Now, only at absolute zero would that kinetic energy go to zero, But otherwise, even at a very low temperature, they possess some kind of kinetic energy. They could be just vibrating rather than having some kind of translational movement, but there will be some motion. Molecules also possess potential energy, and potential energy is the energy that has the ability to do some work. So in this case, when we look at this hammer, and we look at its position over here, or here. Now, we're going to disregard that it's actually moving in this case, but when we look at here and here in this position, this hammer actually has more potential energy. It has more ability to do work. So when it hits that nail, it'll drive that nail in farther. Versus if we started the hammer over here and we hit that nail, it would probably go a lot less farther into the wood. Now, this potential energy, as we hold this hammer, it has the ability to do work. It has the ability to drive that nail into the wood. Now, this potential energy is not driving the nail at this moment because it is just stored as potential energy. We have to convert that potential energy into kinetic energy, the energy of motion, to actually drive that nail into the wood. Now, how does this relate to molecules? Well, like we said, kinetic energy is about the movement of these molecules. It can be caused by the movement of electrons within an atom, the vibration or the translation or rotation of the molecules, just as we saw in the previous slide. However, where does potential energy come in? Well, potential energy is actually stored in the bonds between those atoms. So if we go back to our CO2 molecule, now there are electrons around the carbon, the oxygen, etc. There are electrons that are moving within these bonds, but these bonds are a source of potential energy, and if they're broken, they can release that energy into the atmosphere. Now, again, we can also have another source of potential energy, something that we haven't really spoke about in the previous, is between the nuclear forces keeping the protons and the neutrons together. Now, if we were to break those nuclear forces that they hold these in, we can have a tremendous amount of energy change released from here. So thermal energy, again, is just about the kinetic energy found in these molecules. So what's the difference between thermal energy and heat? Most people say that these are both the same. Heat cannot be possessed. I'll say that again. Heat cannot be possessed. Heat can only be transferred. So thermal energy is something that an object can possess because it is made up of molecules. Those molecules are undergoing some kind of movement. So in this fire or the steam here, the molecules are undergoing moving, and it has a certain amount of thermal energy. However, heat is just the transfer of that thermal energy between objects at different temperatures. Okay? So when we look at something like this over here, this situation over here, this has a certain amount of thermal energy. The vapors that are going in are made of gases. That has a certain amount of thermal energy. It's probably a lot of thermal energy. They're moving quite fast because it's hot. The temperature is hot. Now, your hands may not have a lot of thermal energy, especially if you're wearing a sweater. It'll probably be cold. Heat is about when these molecules hit with the hand and they transfer their thermal energy onto the hand. Eventually, if you have your hands on top of a fire like that, they eventually start feeling very, very warm. And that's because as these molecules hit your hand, they transfer the thermal energy in what we call heat. And heat is denoted by the letter Q. So one thing to note is that heat always flows from warmer areas to cooler areas, just like from the fire into your hands. And it can be transferred in a number of different methods: conductions, convections, and radiation. Same thing happens with this piece of metal over here. Now this piece of metal is gallium, and when you put it onto your hand, it actually starts to melt. Your hand possesses a certain amount of thermal energy, which the gallium does not, and as the thermal energy gets transferred onto the gallium in the form of heat, it begins to melt. Now, there's a lot of different ways we can measure it: joules, kilojoules, and calories. Mostly in chemistry, we'll be seeing kilojoules, but you might also see joules. Calories, there's not the same calories as you see on the back of a cereal box, but they are a form of energy. 1 calorie is equal to 4.184 joules. Okay, so finally we get to temperature. So we looked at thermal energy, we looked at heat, and temperature is now next. And temperature is the measure of the average kinetic energy of the particles of the substance. Thermal is the total, temperature is the average. So the faster these particles move, the higher the temperature, which means that thermal energy, the measure of the total kinetic energy within a substance, is directly proportional to the temperature within a given system. However, there is another thing that we have to take into account: the amount of the substance. So one thing to just kind of think about is how a thermometer works. So a thermometer has a little bit of liquid in here, and let's say we put it into a hot bowl of water. Now these water molecules have a certain amount of thermal energy, aka kinetic energy, and they are going to be moving around and hitting this thermometer. as they hit this thermometer, they're going to be transferring some of the thermal energy to the substance inside this thermometer, and that transfer is going to be what we call heat. And that transfer of thermal energy is going to cause an increase in thermal energy of this substance in here, and we're eventually going to see a rise in what we call our temperature. Okay, so the more thermal energy we have, the more collisions we'll have here, the more transfer of heat, and the higher the temperature. So when we look at these two situations here, we have the water in here, which has possessing a certain amount of thermal energy, and the water in here that again possesses a certain amount of thermal energy. Now, if we were just to look at these temperatures, we can say that this water possesses, in a sense, more thermal energy because we'd expect thermal energy and temperature, it's directly proportional. This one should have more thermal energy. However, what we fail to note is that this one has twice the amount of the water molecules as this one over here, meaning that not only these ones have to have a certain amount of thermal energy to get here, but that means all of these water molecules in here have to get over here. There are more water molecules possessing more energy, and so what we'll have is even though it's at 90 degrees, this one will have a lot more thermal energy than this one over here, due to the amount of water molecules that have to have a certain amount of energy to get it to a temperature like this. So a few definitions that we have to kind of go through. When we talk about systems, what we try to do is we try to isolate as much as possible so that we can just measure the substance in question. And so when we look at that, and let's say we have these substances here, we have a reaction occurring under here, and we have particle A reacting with particle B. The particle A and particle B will be our system. Okay, so there's an energy change happening between these particles. However, all we want to do is we want to try to look at the energy change between these particles and nothing else. Now that's hard to do because this reaction is taking place in water most of the time, and that water is contained in a Erlenmeyer flask or a beaker. That flask is on a table that is exposed to some kind of atmospheric conditions. So all of these things can play a part in the energy analysis of this reaction. So what we want to try to do is we want to try to isolate this system from the surroundings. So in this case, it's very hard to look at just the system and not take into account the water, but that's what we truly want to do. We want to look at just the relationship between these two, not really the waters, and we call that the system. Everything else, the surroundings, the glassware, any kind of metal parts, tools, equipment, that is all called the surroundings. Now if we add our system and our surroundings together, we get what we call our universe. Okay, so everything else. Now, again, our whole point here is to try to isolate the amount of energy. So we want to try to minimize the amount of energy going into our system from the atmosphere, or on the other hand, how much energy is being lost by the system into the atmosphere. We want to try to capture it all and really use it for our data collection. So there are three different types of systems. Now, most of the time, we'll see this kind of system in a high school or even university chemistry lab, where we have an open system where, for example, here we have a pot. The pot is not really insulated. There's no lid over here. So when this water starts boiling, matter starts going all over the place, and matter is escaping as well as energy escaping because it's not insulated. This is an open system because both matter and energy can escape. At the same time, let's say, for example, this was very, very cold and we had a very, very hot pot beside it, energy could be transferred from this in the form of heat into this, and again affect the energy calculations in here. A closed system is one better than our open system. Even though it's not insulated and still allows energy out or in, it helps limit how much matter goes in and out of the reaction as well. The best that we can do is an isolated system. Now, some scientists say that it's truly impossible to get an isolated system because there is always going to be some energy change. But what an isolated system is one that helps reduce the amount of energy that is lost or gained by the system to the surroundings, and as well minimizes the amount of matter that goes in and out. Now, it's important to know whether we have an open, closed, and isolated system because that will help us with our energy calculations. We know that the law of conservation of energy exists, meaning that energy is not created or destroyed, it basically remains constant. What that means in terms of chemistry and thermochemistry is that, let's say for example we had a flask with a system in here, and that system, there's some kind of change in energy over here. We can measure how much energy is, what the energy change between these particles is, by measuring the overall temperature change of the water. Because remember that these particles are reacting within water. If they overall lose energy, that thermal energy will be transferred to the water as heat. And remember that temperature is directly related to thermal energy. So as the water gains thermal energy, the temperature of that water will also increase. So we consider the water, in this case, the H2O, this will be our surroundings, and the chemical reaction, so the chems, this will be our system. So if energy is lost by our system, that means it's going to be gained by the surroundings, satisfying our law of conservation of energy. And that's why this equation over here is very, very important to our understanding of thermochemistry. If this system, for example, is an endothermic reaction, meaning that it gains energy from the surroundings, what that means is that the surrounding water will lose energy, and that means that the temperature will go down. Again, satisfying this equation over here. So thanks very much for watching. Stay tuned. We're going to develop these concepts as we move on through our thermochemistry unit. Take care. Bye-bye.